How's it going, everybody? In this video, we're going to take a look at UDP, what it is, some of its operations, and some of the ways you can work with it inside the network. And if you're not smart, which I know most of you are smart, but in case something does happen and you're not sure why, this is going to be a good video to understand some of the things you're going to run into when it comes to UDP and how to work with it. So, UDP itself stands for User Datagram Protocol. And basically what that means is it uses a connectionless unidirectional protocol where if in the previous video we talked about TCP, and with TCP you have a connection oriented, which means there's going to be a three-way handshake between the source and the destination. UDP is not like that. Where UDP, most people refer to UDP in the voice video respect, but there's other protocols that use UDP besides voice and video. You know, voice being your phone call, video being your telepresence and your WebEx, things like that. Your Skypes and things of that nature. Where UDP operations such as DHCP for dynamic host configuration, DNS for domain name system, SNMP for simple network management protocol, all of these are UDP operations because of the fact that there's really no control plane there's no three-way handshake between them. Where DHCP, you go out, you look for a DHCP IP address, a DHCP server to grab an IP address, a subnet mask, a default gateway, any options that you might need. Say, for instance, like, you know, do you have an IP phone connected to you? Do you need to know, that? Do you have anything going on in regards to the options in like DNS, things like that? So that's basically what you're going to be looking at when it comes to DHCP. But again, they are they're stripped down and easy to work with. That's the main thing. So the first thing we're going to look at is going to be the header. And I don't have any diagrams or anything like that. It's simple enough for people to Google the UDP header. And UDP is an open standard, so it's not like it's Cisco proprietary or anything like that. So you're going to have a source and destination port. So depending on the protocol will depend on the port. So for instance, DHCP uses 67 and 68. DNS I believe is 53. Yeah, it's 53. And SNMP is 161. So these are definitely going to be ports you're going to want to know. And I don't know if they're going to ask you this on the CCIE written exam, which is what we're studying for, but it's possible. The length and the checksum are going to be, they're variably length packets. You know, you could have a packet with 10 bytes with 20 bytes. It just depends on what's going on with inside of the protocol you're working with. And a checksum to make sure that nothing happened in transit, things like that. So let's talk about starvation and what that is for a minute, because if you don't understand the concept behind it, it sometimes becomes a little difficult. And I have some stuff for you guys to take a look at here at the bottom as a reference point if you want to a little bit know more about it than what I'm bringing up. So starvation, really, it's kind of hard to. When I first started researching it, it was really hard to find anything specific. So after a little bit of digging, I came up with some articles, and that's where it became pretty easy to figure out what it was. QoS, for instance, is going to be one of the main things you're going to run into with UDP, because UDP is going to be for voice. Now, TCP starvation and UDP dominance. What exactly does that mean? Well, starvation and dominance. Well, starvation obviously means you're going to go in and take over something, or you're going to restrict the usage of something. And dominance means you're going to overrule it. You're going to have too much going on at one time. So within the QoS mindset, and we'll talk about QoS in detail when we get to both the written section and the lab section, but the written section is going to be more theory, how things actually work, to build upon your lab. So different classes of traffic, a different treatment for each class. So you can have a class map that goes in and it's supposed to match voice, RTP, and I'm guilty as charged. I am a sucker for NBAR, network-based application recognition. And what that means is you simply go in there and you turn NBAR on the device. You go in and you say match protocol RTP. If the device sees RTP traffic coming in, it will match that. It will set that. A class map classifies. A policy map sets what's going to happen, and then a service policy applies the policy. So pretty straightforward and all with all things considered, but that's usually how it works. So taking heavy amounts of TCP traffic and placing them into the same class with UDP. So how would that happen? Well, it depends. It really does. Because of the fact that there's multiple protocols going on in the background, you might have different ports, different applications use different signaling. It's really dependent on your network, and I'd like to be able to give you a clear-cut, yes, a black and white answer, but I really can't because I don't know your network. My network, the one I work on at work, obviously at work, it's very dynamic, and I've been spending the last 2 months or so getting into the swing of things. Spending a lot of time learning the firewalls, spending a lot of time on port aggregation and looking at different ways that you can manipulate this. And we're actually going away from the internally ran call manager servers, you know, your CUCM and CME, things like that you're going to have on the router or like a Windows server, and going off to a SIP or cloud-based solution. So there's a lot of trickiness with TCP and UDP in the network, making sure we're allowing the right ports and things like that. So it's one of those things when you get into your network, you have to understand what's going on at the protocol level. So doing some packet captures, looking at some things, that will definitely help you out. So if you're taking heavy amounts of TCP traffic and placing them in the same class as UDP, it could be a bad class map. I doubt that would be the cause, but it could be. And typically, that's going to be where you're going to have to dig into your network and find out what's going on. If you want to email me, I'll be happy to help you out with that. TCP and UDP placed in the same class responds differently to QoS. So TCP is connection oriented. Obviously, there's a three-way handshake, and it responds to QoS. And then UDP is connectionless, and it ignores QoS. QoS, if you didn't know, is quality of service. So basically, if you boil it down, congestion avoidance. What is that? Congestion avoidance. Well, if you get into QoS, you're going to find out there's two different ways of handling traffic. You can manage it, and managing means queuing it. What that means by queuing is you have a software queue and a hardware queue on an interface. The hardware queue you can't mess with. That's the actual transmit ring going out to the interface where the bits are serialized to the wire, whether it's a serial, optical, or electrical connection like an Ethernet. From before that, you have the software queue, and this is where QoS steps in. QoS is able to manipulate the queue depth. So depending on the type of queuing you use, whether it's class-based or you're using some sort of hierarchical queuing framework or the module quality service command line interface, either one of those or a grouping of those, depending on how you want to work with it, will determine how things are operate in your network. So congestion avoidance, to get back to the original statement, avoidance is going to be preventing any type of traffic in a queue. So avoidance is going to what they refer to as early detection or random early detection. What that means is you're going to go in and you're going to look at random packets and you're going to drop them. Where WRED, or weighted random early detection, is going to look at what the packet is. Based on a weighting, it's going to drop specific packets. So for instance, if you're doing weighted random early detection at an interface and traffic is coming in, you can go in and you can knock out traffic based on its weighting. And if it's TCP traffic and it's going to be some massive FTP upload, you can drop packets, therefore allowing QoS or voice traffic to follow through. Or it could be SQL traffic. Or I'll say Active Directory domain services synchronization. Maybe you're syncing the AD environment. Whatever the case might be. So what ends up happening with this is TCP slows down and gets starved. Okay, UDP keeps going at the same rate and it dominates it. So unless you have some sort of check in place to do this, will determine how you go about implementing it. So a lot of times you implement, everything works great out of the get-go, then during the day normal operations go on, and then you start realizing where some things don't work quite the way that you had either planned them or your configuration is a little off. Every time I implement quality of service in a network and I'm I'll tell the customer or my employer, hey, it should work this way, but I want to keep an eye on it for a week. And at the end of every day, we'll take a look at queuing, we'll take a look at packet captures, just to see what's going on in the network, and we'll make adjustments as necessary, things like that. So TCP slows down and gets starved out, where UDP keeps going at the same rate, dominating. That's where you get into the starvation and the dominance. Dominance, I mean, unless you have a lot of voice calls, but it doesn't necessarily have to be voice. It could be video, it could be some other type of traffic that's out there, but most typically it's going to be voice or video. Video is the most common bandwidth hog, depending on how it's coming into the network. And a lot of times, I work for a Google company, so Google actually owns the company I work for, and we do a lot of Google Hangouts. So, for instance, if there's a network down emergency, or we want to talk about something big, my boss will get on a Google Hangout with, the network engineers, the systems engineers, senior management, things like that, the chief technology officer, people like that will get in a big Google Hangout. And now I'm fortunate. We have a lot of high-speed internet connections where I work, so I'm not really bothered by small T1 circuits. I work for a communications company, so a lot of the stuff we do is, we're in communications. So we've got high-speed satellite links, high-speed microwave links, things like that. So in regards to the Google Hangout, where we have voice and video, so we have an upload going out of, say, maybe 400 or 500K per second, depending on the feed, depending on how rich is it, high def. And then if you're not familiar with UDP that well, most people have high definition TV, especially if you live in the U.S. It's a big deal here in the States to have 1080p. 1080p is Blu-ray high definition TV. I have one TV that can do it. I don't run 1080p. I run 1080i. So one of the newer features, being in the communications industry, is 4K and 8K. Now 1080 means 1080 pixels, where when you get into 4K and 8K, that means 4,000 pixels and 8,000 pixels, which means your pipe, so your internet connection, your upload, because when you're on camera and you're talking to somebody else, you're gonna be uploading your image to somebody else, and they're gonna be downloading it to their computer. When you're looking at rates like that, let's say even a 1080p is, say, 1.5 meg up, so it's a T1 upload. So if your circuit's T1, you're going to have some problems. Where if you have, say, 4K, that might be 5 meg up. That's a big increase. So depending on your network, you'll have to take a look at that. So latency. Let's take a look at latency for a minute. Since voice over IP calls use UDP transmission, latency and delays are absolute killers of voice over IP calls. Jitter and out-of-sequence packets are just as bad. Jitter is a variation in delay, if you did not know that. So what does that mean, variation in delay? So let's say, for instance, that you determine that 50 milliseconds is an acceptable delay for your network, okay? And let's say through network congestion and normal operations, you determine that a voice packet can't withstand more than 100 milliseconds of delay. Okay, well, basically, if you were to look at this and minus 50, that means you have 50 milliseconds would be the jitter. That is going to be the difference in delay. So 50 milliseconds. So some networks can't support that. It just depends on the situation. I mean, every network is different. I can attest to that. I've touched about 10 in the last 8 months working on consulting gigs. But because voice over IP uses UDP, the voice itself is very small and smooth. So it's broken up. The words that are coming out of my mouth, depending on the codec you're using, like if you're using G711, it's going to be 64K upload in most cases, and it's going to use a smooth. It's going to be smooth forwarding. Where if you're going to deal with voice or a video, it's going to be a lot bigger. It's going to be a lot burstier. Burstier in the respect that, and I'm trying to catch myself here with how it actually does work. Burst typically TCP traffic is burstier than UDP, but depending on your connection and any latency that's on the network, UDP video can be a little more bandwidth intensive, and depending on how much latency and jitter is on the network, that can affect it. So if you're watching TV and all of a sudden the picture goes a little wobbly, or goes a little what's the word I'm looking for? Gets a little can't think of the word I'm looking for. It looks kind of staticky, like it's not very clear. Then that is where you run into issues with delay. The delay is end to end. So if you're sending traffic and all of a sudden it gets a little wobbly, or gets it's not very clear, then those are situations where you might want to take a look at your connection. Are you allowing all the right type of traffic to be forwarded? So now, when it comes to RTP and RTCP, RTP means the real-time protocol. So this is what voice over IP uses. This is the actual phone call. It uses the even-numbered ports on a firewall, or a router if you're using a router to do your forwarding. In the company I work for, we use nothing but firewalls on our edge, and I'm 5 or 6 sites into the firewall testing. So what I'm doing is, because I'm taking over for originally the company I worked for, they had outsourced some on-site help. So they had some contractors from another company that working full-time directly at our premise and running the network. Well, the company I work for, we're going back to the in-house, so I'm the very first IT person to get hired on directly since the outsourcing effect happened. Well, the problem we have is I'm going through, and to make sure that everything works the way it's supposed to, is I look at the config, I document it with the engineer that actually put it in place, and I go, okay, this is supposed to work XYZ. He says, yes, it is. We go through it, I make sure, and then within a week, or I usually go through 3 or 4 sites a day, and then I take a look at that, and I go in and I'm able to, I test it on a per site basis. So I'll have the IT person on site come in, we'll do a failover, make sure the things work, and make sure VPNs fail over, that type of stuff. I know it's a little off topic, but just something to be aware of if you're coming in, if you're new to a network, and you're going to be eventually I will become the senior network engineer, and right now I'm in training to become the senior guy. Now where RTCP comes into play, that's the control plane. So it's going to be the real-time control protocol. It's going to use the odd-numbered ports. And RTCP, you can actually see these when you're actually looking at packet captures. RTP will show up as RTP. RTCP will be the same. They are child protocols to the parent protocol SIP, but not in every case. So don't misunderstand that if you're running RTP, RTCP, that you're going to have SIP. SIP is a parent protocol where it handles all of the session initiation protocols, what it stands for, going back and forth between your site and then the SIP server that you're trying to form the relation, the call with, and things like that. So I spent about a week and a half with a 30 phone soft phone and hard phone implementation for SIP, and it was an absolute nightmare. And a lot of this came down to what we're talking about here, so that's why I'm kind of up to speed on it, because of the fact of what we had to deal with. It was very intensive, a lot of packet captures on both sides, our network and their network, spinning up new circuits, buying new firewalls, making sure this and that. Come to find out that, like I said, we run Juniper on the edge, and Juniper, based on the soft phone that was being forwarded to us from the vendor, actually some of the UDP traffic that it would send didn't conform to the RFC the RFC, to where all UDP packets need to be 64 bytes, or our frame needs to be 64 bytes. We were running into issues with small frames, and the Juniper firewall would drop them because it didn't recognize it. So it would drop it, we'd get bad call quality, one-way audio, things like that, or the signaling. We couldn't determine exactly what that 4 bytes or 10 bytes of data was. We could never determine that. But what we could tell was, as soon as that packet was dropped, we'd have some issue with the phone call. So like either the signaling over the SIP provider to transfer the call, control plane protocols would get dropped, or the call would drop completely. And lots of issues. We finally got that sorted out. If you'd like to know more about that, I'd be more than happy to talk to you about it and give you an update if you're troubleshooting a SIP implementation. But that's pretty much where all I had for you on this video. Pretty straightforward stuff. If you are looking for more about it, feel free to check any of these links out. If you want to know more about all of these, definitely check it out. It's one of those things where I would recommend reading up on them. And most people say, well, Wikipedia is bad. No, I couldn't disagree more. I love Wikipedia. Now, it is driven by us, so people in the world that know what's going on. And sometimes it's given, bad info is given, and you have to sort what's good, what's bad. So, my recommendation, read more than one source. So when I'm going through and I'm learning a new protocol, I read vendor neutral. So technology that's not based from a vendor's implementation. So like I don't read a Cisco book if I want to implement spanning tree. I read Interconnections, Radia Perlman from Sun Microsystems. She wrote a book on spanning tree. I read that book. Awesome read. It's a little lengthy, but I really understand how spanning tree works, and that comes into play. So don't read just what I have recommended here. It's what I think would be a good place to start, but you don't have to. And I'm going to start doing this on a pretty regular basis, what I would read and going through my videos and stuff like that. So, and the nice thing about it is we're almost done with our introduction stuff. So all the stuff that goes on in the network that isn't exactly attached to implementation, it's knowing the processes and the protocols and a foundation level of understanding. So if you have any questions, feel free to drop me an email. I hope this has been informative for you. I would like to thank you for viewing.